Okay, thank you.
Okay. Salam guys, I hope you are doing well. Welcome to lecture 16. This is almost the last lecture in which we will learn the design process. Okay, and this lecture is all about metamaterial based antennas. Okay, actually there are many types of the and many techniques in metamaterial. Okay, and we will learn some techniques. Okay, and let's start this session. And I hope after this session we will maybe tomorrow or day after tomorrow we have to decide the design. Okay, this one is just a technique to increase the gain. It is not a part of the antenna. Okay, because antenna, you operate the antenna at some frequency band. Okay, and you just use this technique to increase the gain and to improve the radiation pattern of the antenna. Okay, but the main things, the main antennas are the previous, in the previous lecture we have studied. Okay, so like the flexible human body implantable. Yes.
Or miniaturization of the antenna.
Yes. Also miniaturization. Okay, so the main important types of the antenna other than metamaterial, like reconfigurable, millimeter wave, and other things. Okay, so this metamaterial is just a technique to miniaturize, to keep the size of the antenna compact, or sometimes it increase the size of the antenna. But in the case of the EBG structure, it helps to reduce the size of the antenna. Okay, also we will use this technique in most some of our designs. Okay, to increase the length of the paper and to improve the results. Okay, because with as I told you in the previous lecture, with only if you target only one antenna without any application, it is hard to publish in a good journal. Okay, so you need to have a strong designs and strong data. Okay, I mean, if you have a full length article, then it is easy to target good journal. Okay.
Also, brother Sarosh, yesterday and today, because when I'm making this research review, I found also recently some people use it for the MIMO antenna. Actually, this idea, it was in my mind, but I was afraid, because MIMO antenna, there is a separation between the antenna. If I put a full metamaterial structure, I am afraid this means I need to use full, for example, full sheet for metamaterial, or we can separate for both. For example, if I use two antenna as a MIMO, for each antenna I can put a metamaterial individually.
Yes, actually, if you are targeting the MIMO antenna, then neglect the single element antenna. Okay, only target the size of the full MIMO antenna. Okay, let's suppose you have the size of the MIMO antenna is 60 cross 60. Okay, so you need to create a you can create a MIMO, sorry, metamaterial of the same size of the MIMO. Okay, and if even if you want to use the EBG structure, then you can place the EBG structure in center of the MIMO. Okay.
Okay, thank you.
Yes. So, but most of the cases we take the metamaterial of the same size of the antenna. Okay, but in the case of EBG structure, you can use small, or maybe it help you to reduce the size. Okay. Okay, so let's start with this one.
Mr. Ahmed.
Yes.
Please, did you read my questions about metamaterial?
I did not find time to read the questions. Maybe after this lecture, or I will send you or answer you, or maybe on WhatsApp. Okay. Okay, and maybe in this session. Okay, but I try to explain more. Okay, to give answers of your question.
Okay, thank you.
Sometimes here we do not eat, I mean, it is hard to find halal food here, so sometimes health may you know.
Yes, it is very difficult issue.
So that's why I've got anyway.
You try to cooking with yourself.
Yes, here I cook myself. So that's why, but here, it is very hard to find a halal food, and when you eat some other thing, you will be ill.
Good luck. It's very difficult.
Okay, so let's start the EBG structure. I'll also have simulated some files. Okay, in this lecture we will learn the design process, and I will not simulate the files. Okay, I already simulated some files, and we will discuss the results, because EBG and metamaterial take much time in simulation, more than antenna. Okay, so we will learn the design process, and then we will discuss about the results. Okay, so in EBG structure, actually in metamaterial, as we know, in antenna we apply different techniques, same as in metamaterials. We use different techniques. Okay, we have MTM. Actually all of them are of same kinds, but just a little difference. Okay, MTM, FSS, okay, and the EBG structure. Okay, so we have a MTM, that is called metamaterial. Okay, metamaterial. Okay, and the other one is the frequency selective surface. Okay, there are many names of this one, but the working are the same, working procedure are the same. Frequency selective surface, sometimes we call it FSS, sometimes we call it MTM, sometimes we call it EBG structure, electronic band gap. Okay, okay, so today lecture, okay, first we discuss its working procedure. The all have the same working procedure. Okay, suppose
Excuse me, brother, because I worked before in, as I said to you, in FWS or absorber. Actually, at this time, this structure of metamaterial, we're dealing with it at, like a filter, special filter.
I do not understand what are you talking about.
Because this structure, if you select it as a frequency selective or absorber or any kind of this kind of application, we're dealing with metamaterial, or we construct metamaterial as a filter. Bandpass filter. I get used to dealing with this matter.
Yes, but we can also use in antennas. We can use here wherever we want.
But the filtering effect, I think, is different from enhancing the gain or something. I think that.
No, because I did work on FSS, I did work on MTM, and both have the same procedure. But the difference is that in AMC and MTM almost the same. Okay, in AMC we have a reflection phase. Okay, like we have a reflection phase like this. Okay, we have like this. Okay, so we have a suppose frequency band at 2.45 and 5.8. Okay, in AMC and metamaterial we check the phase. Okay, so we have a phase here. Okay, suppose here it is 0 degree, here it is 90 degree. Okay, and here it is minus 90. Okay, so the total is 180 degree. Okay, so in all of the cases, I mean in MTM AMC, we check the reflection phase of the reflector. Okay, reflection phase. Okay, reflection phase. Okay, so we check, suppose in the case of this, suppose we want at 2.45 gigahertz. Okay, if the phase this is 0. Okay, so if the line cross. Okay, so here we have a 2.45. Okay, here we have a 5.8. Okay, and here we have a 0 degree reflection phase. Okay, so if you create a dotted line, horizontal line, okay, you need to check the point that intersect. Okay, this one and this point and this point. Okay, so at this point you see, if the reflection phase is 0, then this one is works for the I mean this case is for the MTM and AMC. Okay, are the same thing. Okay, in this case you check the reflection phase and it must be 0. Okay, 0 degree at the desired frequency band. Okay, okay, but in the case of the and also in this case it is hard to achieve the wide band or broadband. Okay, because in this phase it cannot be like this. Okay, like you want this is your horizontal axis. Okay, so this is your frequency and this is your phase. Okay, so at 0 degree it cannot be a horizontal line. Okay, I mean this one, this line. Okay, so that's why in AMC or MTM we mostly use this one if we have a multi-band, dual band, or single band antennas. Okay, but in the case of the EBG structure and FSS, here we can achieve the broadband. Okay, like in this case we check the like we have a phase. Yes, we have a phase. Okay, okay, so here we have a frequency. Okay, this is the case of the AMC. Okay, artificial magnetic conductor. Okay, here let me write the name, artificial magnetic conductor. Okay, we have four names. Okay, the first one is MTM, metamaterial. Okay, FSS, frequency selective surface, EBG, electronic band gap, and AMC, artificial magnetic conductor. Okay, I will send you the papers on all these types. Okay, and there are a lot of papers and videos available and lectures available on these types. Okay, I will send you these papers so that you will more clearly understand. Okay, so in the case of the AMC or metamaterial, okay, we have a reflection phase. Okay, this is the reflection phase, and on the vertical axis. Okay, and sorry, not here. Okay, okay, on the vertical axis we have a reflection phase. Okay, and in the case of the horizontal axis we have a frequency. Okay, okay, so in the case of the AMC or metamaterial, we check the reflection phase and it must be 0 degree. All the cases, in all the cases it must be 0. Okay, like in all the cases, okay, it must be 0, but the difference is here you check the phase. Okay, like in CST, if you open the CST like this one, this is AMC or metamaterial. Okay, so here you have S parameter. Okay, you need to check the phase. Okay, and you see here you have a degree phase. Okay, this is the reflection phase at the vertical axis, and this is the degree reflection. Yes, and on the horizontal axis you have a frequency. Okay, and it must be 0 at the desired frequency band. Okay,
why must be 0?
Yes, in all other, and if you talk about the other angles, because it will not like you in reflection coefficient that reflects. Okay, at the desired frequency band. If you're talking about, like, if you have S11 of the antenna, okay, it is reflecting at suppose 2.45 gigahertz. Okay, if you are using the MTM or any metamaterial technique, if you have a 0 degree reflection phase, then it will not reflect this one. Okay, it will only work at it divert at the other frequency bands. Okay, and at the at the desired frequency band it will not divert this S11. Okay, this reflection coefficient. Okay, so that's why it must be, the phase must be 0 at this point. Okay, and it will give you high gain at this point. Okay,
frequency selective surface we do the same, because if you draw both in the same figure, we'll find the reflection is 0. Add to your point of interest.
yes, this is the AMC unit cell that is published in the paper. Let me open the paper too.
Mr. Ahmed, I have confusion. Why when you verify or check is this unit series AMC or FSS, not check from permittivity and permeability? Why?
Actually, as I told you, both have the same.
Because you are verified from the phase of S11, not from permeability and mu.
Yes, here in AMC and MTM we are checking. Yes, in most of the cases we are only check the phase, not the relative permittivity. Okay, sometimes but in research, I think, yes, in research they use relative permittivity. Okay, in the case of the electronic band gap and FSS. Okay, but here my mostly work is in AMC plane. Okay, this is AMC back antenna. Okay, and MTM.
The definition of Metamaterial, he said you must the mu and the epsilon must be negative.
Epsilon
permeability and permittivity.
Yes, maybe I because I mostly work in the AMC plane in the case of the reflection wave, but I did not calculate any with epsilon or relative permittivity or relative permeability.
It's for SWS, it's true. It must, but we cannot say, I think, in all the frequency range. Maybe in some frequency range can be negative.
Yes, the other thing is that if you are designing the antenna substrate of FR4 that has the relative permittivity of 4.3, then you must need to use the same substrate. Okay, in the case of the metamaterial, any artificial magnetic conductor, EBG, and many things. Okay, so you need to use the same substrate. Okay, in that case you have the same relative permittivity.
But Sarosh, actually, I work in FWS. But I want to ask you one thing. This four kind, AMS, I don't work in it. I hope one day. But for the when I design these four types, I want to confirm from you the excitation. How I can differentiate the excitation, setting up.
You are talking about the ports, assigning ports.
The boundary condition. I want to differentiate between metamaterial, FWS, and also the AMC. And the port. I think the port is the same. I don't think so.
Okay, when we design and assign port, then we will discuss it. Okay, in the case I will share another video of Mr. Ihab. Okay, I told him to share the videos with you. I will send him your emails. Okay, he will share with you by email, the email on the YouTube channel. Okay, because his main work is on FSS. Okay, and my main work is on AMC and metamaterial. Okay, but we will discuss.
But I start confusing. If I make a metamaterial, I can't excite by the same way as if it's.
Yes. In actually there are many ways. Okay, let me draw here. Okay, in the case of the AMC, if you talk about the AMC or the metamaterial MDM,
yes,
you have a EBG unit cell here. Okay, and you have a let me draw here. Okay, so suppose you have a this is a unit cell. Okay, unit cell. Okay, in the case of the AMC, you have a port in front of the radiator. Okay, in front of the radiator. If you want to use the metamaterial, I mean, if you want to keep the antenna in front of the unit cell. Okay, like this is your unit cell, and if you are converting into array. Okay, of unit cells. Okay, like there are so many, you copy paste. Okay, I mean 2x2 array or 4x4 array. Okay, so in the case of the AMC and metamaterial, you have a port in front of the unit cell. Okay, in front of the unit cell. Okay, because you are placing the antenna in front of the metamaterial. Okay, like this one. Where is the, yes, like this.
Yes.
Okay, this is your metamaterial. Okay, this one is your metamaterial, and this one is your antenna in front of the metamaterial. Okay, so but in the case of the EBG structure, there are many ways to simulate the EBG structure and FSS. Okay, you have a EBG unit cell. Okay, here. Okay, it also depends on the some people suppose this is your antenna. Okay, and some people like to use the metamaterial behind the antenna. Okay, like this is your metamaterial or MC behind the antenna. Okay, so some people like to use the metamaterial on the left side or right side of the antenna. Okay, how can I draw 3D here?
Yeah, I saw some paper using.
Yes, suppose this is your antenna, and people use metamaterial, like this is your metamaterial or AMC or whatever. Okay, and its direction is in this way. Okay, and its direction is in this way. Okay, some people use metamaterial in this way. Okay, this is your antenna. Okay, and some people like to use metamaterial in front of the antenna, some in behind the antenna, some on the left and right side of the antenna, some on the top and bottom side of the antenna.
What on the, I think, of course, the pattern of the antenna. But antenna, the pattern, if you want to enhance it, it become above the antenna. For that, you need to put the metamaterial above. Or if you want to use maybe the side loops.
Yes, in most of the cases we place the metamaterial in back of the antenna or inside the substrate of the antenna, okay, like a EBG structure, okay. So that's why there are many ways to simulate the universal, okay. So but here we are going to learn only two ways, okay. This one, okay, that is behind the antenna, because we mostly use this technique. We don't use this one, okay, this technique, okay. And other thing is that like you have a structure here. First you design the EBG universal, okay. Suppose you have designed the EBG universal, then you convert this EBG universal into arrays, okay. Into arrays, and then sometimes you create a strip line of the same size of this length of this length, okay, this length, okay. And then you create port here, okay, and then simulate this array, okay. But in the this is other technique to simulate this EBG universal, okay. And some in some of the cases this is universal and they create port here, okay. Here is one port and here is another port, okay. And there are two ports, left and right side of the EBG universal, okay. Some people simulate in this way, okay. So there are many ways to simulate universal, but we will move towards the easiest way, okay.
But all of them will have the same result. For that, I confuse about another type other than FSS.
Yes, all will have the same results, okay. Because no, not I mean in the case of the like a reflection phase, okay. I'm not saying that that you if you are simulating on the, yes, in the left and right side, then yes, the reflection phase must be 0, okay, in that case, okay. In EBG universal and FSS you are able to achieve the broadband, okay. But in AMC and in metamaterial it is not easy to achieve broadband, okay. But in the case like this one, this is AMC or metamaterial, and you see here is a reflection phase, okay, and it is 0 degree, and you see it is only at one frequency band, okay. And even if you check this one dB, you will see like this. Suppose this is your S11, okay, and in this case you will have two dual resonance, okay. But in the case of the EBG universal, you have the S parameter, okay, and in this case you are able to achieve the broadband, okay. And you see it is even if it is very close to 0, then you can say that this is your broadband universal, okay. You can implement this universal for the broadband communication, okay, like for UWB antenna, okay. So in this case you see it is not exactly 0, but it is very close to 0. Suppose and you see this is a multi resonance universal, okay, like this one. You see it is resonating at this point, this point, this point, okay. And only at these points the reflection phase is very close to 0, okay. If you see at this position, like at 5.57 gigahertz, then the reflection phase is close to 0, okay. And also this one, okay, and in only at that frequency band, okay. Like maybe this antenna is a tri-band or for a quad band antenna, okay. And in this way you can achieve a broadband. I think I had a UWB universal, but not sure.
UWB?
Yes, there is a UWB universal. Let me check.
If you want to get UWB, you must make, I think, many layers.
No many layers. Let me check here. I have downloaded, and also at the end of this session I will share all the these things, okay, these things, okay, MTM, FSS, ABG, and AMC. I will share the CST files. You don't need to draw again. You just modify the shape or increase or whatever you want. Like you want another substrate, you can modify this one, okay. You can just change the dimension of the substrate, okay, and use different material and change the shape, whatever you want, okay.
And HIS.
I don't know what is this. Can you abbreviate this one? I
It's
think
metamaterial.
yes, but I did not work on it, okay.
Also, we have another thing. DNG also double negative.
Yes, there are many names as I told you, but we are specific only this one because metamaterial AMC universal. Okay, we will work on this one. Okay.
But actually, I want to appreciate the way of the excitation.
Yes, I will share the all the files. This file EBG universal and AMC universal. Okay. Yes, I will share 3 files with you. Okay. In different ways. Okay. This is for dual band. This one is for dual resonance, okay, like you can see here the phase, okay, and even you can, if you you can make it a tri or multi-band, okay, by modifying the shape, okay. And for the EBG universal and also the CST file of the broad UWB universal, okay. I am checking here if I find here.
Mr. Ahmed.
Yes.
I have until now confusion. Why some people use time domain solver and some people use frequency domain solver for simulating unit cells?
Oh, okay.
When I test to make the same unit cell in two different solver, I get different results.
Yes, surely you will get different results, okay. But in the case of the only if you are designing the unit cell,
because I always use time domain solver when I make unit cells.
Okay, but in the case of the unit cell, only to design the unit cell you need to use the frequency domain solver, okay. But in the case of the when you are simulating the antenna and the unit cell together, then you need to use the time domain solver, because if you are implementing like if you are designing the unit cell and you are using the frequency solver, this is in frequency domain, you cannot fabricate, you can fabricate, but you cannot get the results of this one, okay, in frequency domain. So you need to go to the time domain so that you can fabricate and measure these type of unit cells, okay. So when you are dealing
time domain solver and in the time domain solver, I have also big problem with the boundary condition, the correct boundary condition.
Okay, we will discuss, we will start we will start the design process of this one and how to assign ports, okay. I will show you. First let me have a look to the broadband.
You will simulate it in time domain or frequency?
I simulate, if I am only simulating the unit cell, then I used frequency domain, okay.
Not time domain.
No time domain. But if you are simulating dealing with the antenna and the EBG unit cell together, then you will use time domain, okay. Just keep in mind.
Yes, of course.
Yes, this one is the UWB EBG cell, okay. I will share with you, okay. This is
this kind of port, brother Sarosh, actually is made confused. Sometimes you use one port or sometimes 2 ports.
Yes, actually this is the EBG unit cell, okay. Here they have don't okay, let me explain in what case we need a dual port and in what case we need one port, okay. Just let me, okay. If you notice that there is a ground plane, yes, behind the unit cell. If there is a ground plane on the behind the unit cell, you only use one port, okay. Just keep in mind, okay, because if
So
you
this-
have a
in this
full
case
ground
is
plane,
a reflector.
what?
So in this case is as a reflector.
As a reflector.
Yes, because if you are using the full ground plane, then there will be no effect of that second port, okay. So in that's why I have used here one port. Just keep in mind, okay. If you are dealing with if you don't have a ground plane on the behind the antenna, sorry, unit cell, then you need to use 2 ports, okay.
So this is EBG example, yeah?
Yes, this is
You don't
example.
need to use a ground plane behind the cell.
you can use, okay, you can even use ground plane if you don't like, suppose, let me explain. Okay, let me explain.
How we can the good result? What is the better, using ground or not?
Okay, let me explain more about, like, you have antenna with full ground plane, okay, and
Yeah.
there is a ground plane behind the antenna, okay. So in that case you are preferred to use the EBG or whatever metamaterial with full ground plane, okay, because if you in the case of the EBG structure, if you want to implement the unit cell on the, like, on the top side, or on the center of the antenna, then it will have the ground plane, okay. And if you have a unit cell, okay, like this one, and you have a full ground plane on its back, okay, and it will help you to increase the gain, okay, because in front of it you have antenna, okay, and all the field, E field, okay, will be in this direction, okay. In most of the cases we have a big size of the metamaterial like this one, okay, you see this is a bigger one, okay. And I also show you, I mean also tell you that you see in most of the cases we use metamaterial like this one in straight, I mean not rotated at some angle. Here in this paper I have rotated the metamaterial at some angle of 45 degree, okay. So in most of the cases we do not rotate metamaterial in some angle, okay, we just keep at this position, okay, and suppose this is your antenna, okay, and you have a reflector behind the antenna, okay. So I will also discuss its reason why I rotated this one, okay. And because in metamaterial when you place the like you have a multi-band antenna, okay, it is very hard to when you use the metamaterial, then it will help maybe you have designed the antenna at 2 frequency band, okay, and you have used the metamaterial, okay. In my case, when I use the metamaterial at an angle of 0 degree, like I did not rotate this metamaterial, okay, this place in this position, then my only 1 frequency band is working while the other is not, okay. So that was the reason. When I rotated at some angle, like at angle of 45 degree, then I realized that my metamaterial start working at both frequency bands, okay. Here I have added this one, okay, you can see here at 0 degree, this is the below one. Where is the below one? Yes, can you see the below one?
Yeah.
This is the below one, this line, okay, this line, it is not working at 5.8, it is only working at 2.4 with very less return loss, okay. So that's why when I use the red one at 45 degree, then I got good results, okay. And also other results like at 60, 15, 30 I got good results. But why I only use, because I need to keep in mind the feasibility in the case of the fabrication of measurements, because even we can use this metamaterial at an angle of 0 degree, and it is easy to place the metamaterial behind the antenna, okay. But if you rotate, it is hard in fabrication to rotate this one, okay. That's why I have used 45 degree here. In this case it is even little bit easy to place the metamaterial at an angle of 45 degree, but at the angle of 60, 15, 30 it is not easy, okay. So sometimes you will face this problem, you will surely face this problem in the case of dual band or multi-band, that your metamaterial is not working very well, okay. So maybe you can try this technique. I have just find the solution of that problem, okay. That's why I was able to publish this paper.
And Mr. Ahmed, how to place antenna with the metamaterial when you fabricate?
Okay, there are many ways, okay. Like you use foam. Do you know foam?
I never because I didn't have
بتاع الابيض يا طارق، اللي هو بتاع اللي بيغلف الاجهزه.
Okay.
Yes, we use foam, okay, and yes.
You mean this foam? As I know, foam. You mean this is a white and light thing which it can cover, I think, any device in it. Yes, this is a foam. What you mean? This white thing?
Yes, this has epsilon value of 1, okay. This is white foam. okay, or maybe color, it may be different colors, but it has relative permittivity of 1, okay, so it will not affect your antenna, okay, so you can use this form.
It's similar to area.
Yes, suppose this is your antenna, okay, and okay, let me explain more why we need a form, because in most of the cases we use metamaterial along with the antenna, like this is your antenna, okay, like this is your antenna, and you keep the metamaterial with the antenna, okay, like this, okay, there is no space between them. But in my case I use this is my antenna and this is metamaterial, okay, and the distance between the antenna and the metamaterial is 10 millimeter, okay. Okay, so in that case you need a foam of 10 millimeter, okay, so you can place the foam here, okay, as I shown in this figure. Where is this? Yes, this one, okay. So this is your antenna, this is your foam, okay, and this is your AMC plane, okay. So I simulated with many distance, okay. Also I simulated with like my antenna has very small size than the metamaterial, okay. In most of the cases we try to achieve or get the small size of the antenna, okay, because I simulated with the 2 by 2 metamaterial, like this is 2 by 2 metamaterial, okay. I tried with this one, okay, so I got this result, 2 by 2 array, the red one, okay. Where is the red one?
Almost it's the same,
Wait a minute, I think the reviewer did not yes, I think let me see.
4 by 4.
Yes, I use which one?
4 by 4, I guess.
Actually here I did a mistake. Actually this is the results, okay. This is 3 by 3, okay, and this is 2 by 2, okay. The green one is the 2 by 2, okay, this one, this is for 2 by 2, okay, and the red one is the 3 by 3, okay, and the blue one is the 4 by 4, okay. With 4 by 4 surely the size is very big, okay. So I did not prefer to use this blue 4 by 4, because even if I achieve the same results with the 3 by 3, then why I used 4 by 4, that's why I did not use this one, okay. And with the 2 by 2 you see there is very less reflection coefficient, and even I use the table, you can see where is the table. Yes, this one, you see the gain, there is a difference in the gain. With 2 by 2 the gain was 1.89 at 2.45, and the gain at 5.8 is this one, okay. And with the this is
almost not big difference.
wait a minute, what happened this one? I uploaded the same paper I don't know why.
It's very closer to the
no, actually this is not one. I updated the table, but don't know why. Maybe this one, or maybe this is without wait a minute. I don't know why. Actually I in my other paper, let me see the other version of the paper. This is the published one.
How to get the distance between antenna and metamaterial?
You no formula, just to simulate. You check, you simulate multi times, like what happened with the 0 millimeter, 5 millimeter and 10 millimeter, okay.
What is the limit, the distance limit?
If you increase the distance, okay, then you see your antenna profile will not be very thin, it will become a very thick. So you need you need to keep the distance as less as possible, okay. So
what is the less distance I must do?
Lambda
by 4, lambda by 2.
You can use distance of 2 millimeter to 15 millimeter, okay, it is better. Don't exceed with the more than 15 millimeter, because the size, you know, the size of the thickness of the antenna will become, because the thickness of the antenna will not count this substrate, okay. then you will count the whole antenna, okay, like with foam and with metamaterial and the thickness of the substrate, okay.
The body will become bigger.
Yes. I actually I think so that this paper
For the form, where I must drill the form.
what do you mean?
What I must put, I mean the whole of the form in the metamaterial and the lab.
In CST you don't need to use the foam, but I am talking about in
I
the
mean the fabrication, when you fabricate.
yes, you just need
Position
to
of
use
the
the foam behind the antenna, okay, like this is my antenna. Where is this one?
Because the foam has same property as the air.
Only this one, okay, only at this point you can use foam, okay, don't need to use the whole complete form of the size metamaterial, okay.
You know, brother, I saw some people maybe in big size they're using some screw, maybe make from some material. Some people use screw.
Yes, I see the
Yes,
screw.
screw, but here you can see where you can use screw. Here you already have a very small compact size of the antenna, and you even if you use a screw, then it will disturb your results. So if you have a good I mean if you have a bigger size of the, like, let me show you one paper with the screw, okay.
I think it must special material for the screw.
No, actually they use 3D printer to that has the material they have used very less permittivity, okay. Where is the paper? Dual layer for four.
It is similar to using the you know when
Like this one.
We don't use the antenna by hand sometimes. For that I bring I design something like a stand made from the wood to
Yes.
put my hand away.
So here they have used a screw here, okay.
Yes.
Yeah, this is a special screw, okay, that has less I mean permittivity same as in the air.
And I use rubber sometimes. What about the rubber?
No, and rubber may disturb your results because rubber has a relative permittivity of up to 2 to 3 in the range, okay. Because in my
I use maybe a strip of rubber to fix the antenna with the foam. It will disturb also.
Yes, rubber will disturb your results. Okay, because in the case of the my antenna for smartwatch application, surely I have an antenna, and when I embedded the antenna on the smartwatch strap, the strap is made of rubber, and my results may have difference in the results. So that's why I do not prefer to use rubber as you can use foam or this screw, okay. But for the screw you need to create a hole in the substrate, okay.
Is it change the result?
If you are creating the holes in the substrate, then they do not affect your results. But if it is touches your copper, I mean this one, like you create a hole at this position, and surely your results will will change.
And for this material of the screw, what is material?
Actually this is I'm not I don't know, I forgot the material name of the material, but this is these screw are made by 3D printers.
How much?
Epsilon is equal to 1.
Must be.
Yes.
Okay.
Actually sometimes when you submit the paper, then maybe because like you have submitted the final version, and then you after proofreading actually I think this paper is wrongly published. I mean I updated the table. I don't know why this one they have used this one, because at this position I use 4 point, I think so, 4.9 and 4.97 here, okay, but here they have published 1.96.
I think it's maybe in typing itself, mistyping or something. Sometimes happen.
Yes, I don't know why, because I use this one here 4.96, okay, and you see the results are very close to this one, okay. That's why I neglect 4.4 cross 4 and I use this one, okay.
Yes.
And I here you can see
because it's logically when you put this metamaterial, you must improve it again.
yes,
logically.
And here this is the distance you are talking about, okay. This distance,
Yes.
this is the distance, the form, okay, the size, I mean this is your antenna, this is your metamaterial, and this is the distance between the metamaterial and the antenna, okay. So if you increase or decrease the distance between the metamaterial and the antenna, your results, you will see your results will have change, okay. So even if you are using like if you increase the distance, your results will improve a lot, your gain will increase a lot, okay, your radiation pattern will increase a lot, but we need the distance as less as possible.
And why for the high frequency you will get the high gain?
Which one you are talking about? Suppose like an
I mean
example.
when you simulate antenna at 2.4 and
Mhm.
simulate antenna at 5, you will get more gain at 5 without metamaterial.
You are talking about the less frequency band, more gain at less frequency band.
Like in your table, the previous table.
Okay. Okay, when you increase the frequency, your gain, actually gain is directly proportional to the frequency, okay.
You will get more of a gain.
Yes, that's why at millimeter wave band it is necessary to have more than 7 dB when you are approaching to higher frequency band, okay.
Exactly, that's
So that's why gain is directly proportional to the frequency. If that's why if you have antenna like at very like at 900 megahertz, you will not have much gain, okay. So you only have a high gain at the high frequency band, but now they are doing research. That's why they have you introduced the metamaterial and other techniques like antenna array to achieve high gain at the lower frequency band, okay, like sub 6 gigahertz frequency.
because when I simulate antenna at 60 gigahertz, I get gain with the 8 dB. It's very good.
Okay, so now we simulate, I mean we design this unit cells, okay. I will also share these files, okay. You can just assign the material, change the material, and you can use whatever you want, okay. I mean you can get the results, okay. In this case you need to check this one, okay, reflection phase, it must be at 0, and in this case you have a S parameter, okay, and you need to check it if you are targeting the broadband, okay. So and also we can check this one, okay. And in this case you can check this one, you see this is very close to 0, okay. And also this one, if you see this one, you have wide band, okay. So this is working at this position, but you can say that this antenna is for broadband or UWB application, because at the whole frequency band it is from 3 to 12 gigahertz, it is very close to 0, okay. This one,
This is 1.1 or S2.1?
I am talking about this one, S11, okay. This one,
Frequency selective configuration. This one.
S22 and S11, okay. So it is close to 0, okay. So in this case you see this is broadband, okay. So I will share this file with you, okay. You can but you do not publish this one because they are already published, okay. And but you can modify this shape, okay. You can change this shape, okay. You can modify some shape, okay. But you already have ready made these files, okay. I will share these 3 files with you.
Why you get S2.1 less than -10?
S21, you are talking about S21?
Yes, why you get less than -10? That means that this unit cell is not work at this frequency, or?
No, you see in the case of the same like this EBG unit cell, okay, like you have this one, okay, and you don't see this one, this S21, you only see this one, okay. It approaches to 0 or very close to 0, okay. Even if it is very close to 0, then you can say your unit cell is working very well, okay. But if you have a like this one, this is not very close to 0, so it may not give you more good results, okay. But in this case it is very close to 0, so in this case you can say this unit cell works very well, okay.
I mean, why you get S2.1 is close to my at 7 gigahertz, less than minus 10. What's the explanation?
In this position, okay, forget this one, this frequency band, because just see, this is a wide band, okay, and here we do not check this S21, okay, we are only checking this one, okay, because when you simulate you will get different results, and surely you not get desired results, okay, so you need to improve that one, and in some of the cases you only target that results that you need, okay.
Okay.
So I will share these files with you, and also we learn how can we draw these types of unit cells, okay. So let's start with this one, and we also keep the try to keep this unit cell behind the antenna, okay, to show you how can we keep the unit cell, okay. There are many ways to design the EBG or whatever you want, okay, like we can also select this one, okay, like in you can use this one, okay. And for the other, you can also go to these periodic structures, okay. You have FSS metamaterial, in this you can design this one, okay. So you need to just follow these steps, okay. You need to select this first one, go to the next, and you need to select this one, phase reflection diagram, click on the next, and you need in frequency domain, okay. Okay, here you need to select the frequency band, okay, like 0 to 17, okay. Suppose to forget this one, okay. Okay, so you will find this one like this working plane like this, okay. Now you click on the substrate, okay. So you need a unit cell substrate, okay. And keep in mind, when you ever are designing the unit cell, you need to keep the length and width of the unit cell the same, okay. Like this is your unit cell, the length is must be the same, like of 7 cross 7 millimeter or 8 cross 8 millimeter, okay. Because in the case when you will convert this unit cell into array, okay, all will be of the same size, okay, and you will get the 3 by 3 array very easily, okay. 4 by 4, 2 by 2, okay. But in the case of if you have like this size, then it will be issue for you to convert into 2 by 2, okay. And you will surely you will not get I mean this one as the same, it surely its dimension will also be different.
And what do you think about when you use this unit cell without substrate, just a copper?
What, can you repeat?
I mean, when you use these unit cells without substrate, just a copper, like I send you this.
Yes, I remember now. You sent me your paper to you wanna publish them, but in that case, what idea was in your mind to don't use substrate?
I get this advantage in many books. They talk because
Yes,
when you use
I know because there was a customer came to me
shape,
about 1 year ago. He has the design. Let me, maybe I have here. Where is this one? He used a box, okay, with copper, only copper, and was
yes.
amazing design. That was a circularly polarized antenna. Where is this one? I don't know why. The pictures are not here, okay, but he used the box, okay, 3D box, okay, made of copper, okay, that helped, maybe he used that box like this is he used the antenna like this. He used the antenna, this is the his antenna layer, very small size, okay, and this was the circularly polarized antenna, and he used the 3D box, okay, like maybe I think so, maybe he used the that box as a metamaterial, okay, like these sides, okay, on these sides, and then on this side, okay, he used a 3D box, okay, in different way, and he achieved the gain at lower frequency band more than 7 dB. I think the design has 2.45 gigahertz. He only used the copper. Okay, we fabricate that design with very difficulty. So that's why because it depends on, you see, you you send me the paper to design to fabricate, but as I told you, we don't have a facility to fabricate only the copper. So that's why we use substrate. Okay.
Yes, exactly.
And even that paper may not be published yet because of no fabrication in my facility.
Yes, this is a big problem. Yes.
So whenever you are designing, just keep in mind the availability. First check the availability that, yes.
There are some, excuse me, if I design from the beginning as a unit cell, I can bring the antenna easily, yes? If I design the antenna in another file, I can just copy and paste as you show to us by using the coordinate system, yeah?
Yes, we can copy.
Yes, and it will work.
Surely.
Facility, because it will work because I need to change from the frequency domain into time domain. I will make the result again. Yes. Yes,
it will work. I mean, surely it will work. But in you use time domain, you know, when you are going to implement that in a experimental. Okay, like I mean experimentally to fabricate and my year. So you use time domain. Okay.
Yes, I mean, because now we are in different environments. We are in the platform of the frequency of the unit cell.
Yes, we will do. We will do in few minutes. Okay.
Okay, thanks.
Now it is in frequency domain. Okay. Okay, so you have a substrate here. I use FR for substrate. Okay, and I am using what do I use? Okay, 8x8. Okay, so this is the, oh sorry, I use the thickness of the substrate, not 8, 1.6. Okay. Oh, okay, so this is my substrate. Okay, so in this case this is the same case as this one. Okay, so you have a two ports, okay, in front of each other, I mean on the back side and on the front. Okay, so in that case you can say this is your unit cell. You just need to design the radiator. Okay, I mean patch. Okay, we design the patch. Okay, I am align my WCS at this position. Okay, and I use one more thing. You notice in each unit cell there is a boundary, like this one. Okay, like you, if you see this one, you have a boundary, this one, this outer boundary of the copper. Okay, and also in this case, okay, this boundary, and also in this case, like this one, this the outer boundary of the copper. Okay, and you see there is a spacing between them. This one, you see there is a spacing between the substrate and the copper. Okay, and also in this case. Okay,
actually this also need to be optimized, I guess.
Actually
it must be to be what I think lambda by 2 or lambda by 4. I think
I am talking about this one. This, you see that distance. You actually, when I designed this unit cell, I realized that if I create any slot like in the middle of the patch, okay, it does not affect much on my frequency. But if I only increase this length, okay, I mean the width and length, it helps. I mean it shift my frequency a lot. Okay, so in this case, whenever you design the unit cell, it is very helpful point for you. You can, if you change this, I mean the thickness, I mean the width and length, you will have a change in the frequency.
So at the edge of the patch.
Yes, at this point. But in this unit cell, this is a dual resonance unit cell, because this we have two this is a circle and this is a rectangular. Okay, so the circle one, I think, works for the lower frequency band, and the outer rectangular shape patch works for the 5.8 gigahertz. Okay, and this is a miniaturized. Even this is, it has very less small size. Okay, it has a size of 14 cross because you know, even if you design the antenna at this dimension, using this I mean at the same dimension, you will not get a dual frequency band. Okay, even this unit cell works as same as you as antenna. I am talking about the size. Okay, if the size is very small, surely it will operate at the higher frequency band, maybe at 28, 38. Okay, but I have used this dimension, and I was able to achieve the dual resonance frequency. So in this case, that unit cell is a miniaturized unit cell. Okay, and I show you the design step of this one. Okay, you can see here I first use this one, full copper. Whenever you design, you need to use the full copper. Okay, and with this copper I use this one. Okay, and I saw notice that it is only working at 3.5 gigahertz. Okay, you can see here this is your central point. I zoom it. Okay, so this is, you see, this is the zero reference point, and this is the point, and this is the frequency. Okay, so it is working at 3.4 gigahertz. Okay, with full copper. Okay, and then I use the horizontal. Okay, okay, I use the horizontal.
At this frequency, that mean is reflect the waves.
At this frequency, at this frequency, the phase is 0. Okay, like if you implement this unit cell behind the antenna, it will not divert the reflection or do not affect the reflection coefficient of the antenna. Okay, while at the other frequency band, like at 3 gigahertz, it does not show any performance. Okay, this unit cell is useless at the other frequency bands. Okay, like at 3 gigahertz or 4 gigahertz. Okay, we only check at point where it is showing zero reflection coefficient. Okay, okay, so in this case you can even design the unit cell. Okay, when I try to, as I told you, even in antennas, when you design any shape, you just you can also design any new shape in this radiator. Okay, same as in the antenna. Okay, let's delete this one. I mostly, when I design, I use this one. Okay, okay, so let's draw this one. Okay, let's draw some other shape. Okay, okay, first you can create the boundary. Okay, you need to use the copper. Okay, this is my copper, so I create slots in it. I am just showing you these steps. Okay, to design the unit cell, but if someone don't even understood, then I will share the files with you. Okay, you can just directly, you need to only design the shape of the radiator. Okay, and to change the properties or material of the substrate if you want to change. I have many new ideas for this unit cell. Okay, in terms of novelty. Okay, I will share at the end, because we saw many unit cells, but we did not see any reconfigurable unit cell. Okay, what if we use a reconfigurable unit cell? It will be amazing idea.
I think in the fabrication and devising become a very big issue.
Not issue, because I saw one paper, they only use the capacitor. Okay, because the diodes are of the same size of the capacitor. Okay, so you can maybe you are using the unit cell. Okay, like this one, and you are using the patch. Okay, like this is a patch. Okay, like this. Okay, and this is another patch. okay, and you can use a diode here, okay. Maybe when diode is on, it becomes dual band, okay, at 2.45 and 5.8, and when diode is off, it works at 3.5 gigahertz. So in this case, you also need to design antenna that works in this condition, okay.
Yeah.
So maybe we do not focus many frequency band. Maybe we only focus like when diode is on, it works at 2.45, and when diode is off, it works at 3.5. We also need to design that kind of antenna with diodes, that antenna when diode is on, it works at 2.45, and when off, it works at 3.5, so that both antenna and the radiator works together, okay. And also because in that case, like you have antenna, okay, and it is only working at 2.45 gigahertz, and your resonator is working at 3.5 gigahertz, then this is useless. I mean, the unit cell at 3.5 gigahertz is useless, because it is not working at this position. It will not give you any performance at 2.45. Okay, so this is a patch. Let's cut this slot, okay. This is a slot, okay. Okay, let's leave it, okay. This is a radiator, okay, suppose, okay. Now let me remove this one, okay. So you have a radiator, okay, and I need a full ground plane, okay. I pick points, okay, go to the brick right here, minus TP, okay. This is a full ground plane, this is the ground, okay. Okay, so this is the ground plane, okay. As I told you, if you are using the full ground plane, then this point, this position will be useless if you assign port here, okay. So we need to remove this one, okay. So how can we remove this one? First we need to go to the simulation. We need to check the boundary, okay. Background, okay. Let me check the boundaries, okay. So we do not need this one, okay. So we can go to the actually maybe you can see here there is option or not. I think this one is the, let me draw here, okay, this one, okay. This is your boundary, and this is a unit cell in between them, okay. And this is Z minimum, okay, Z minimum, okay, and this is your Z maximum, okay. So Z maximum, this is your patch, okay. This is your patch, okay. So Z maximum is in front of the patch, okay, and the Z minimum is in the behind of the behind the ground plane, okay. So we do not need this one because we are using a full ground plane, okay. But if you are not using the full ground plane, then you can keep this one, okay. But in this case we are using a full ground plane, so this one is useless. So we can use ET. If we click this one, you can see it will only give us I mean ET at 0 degree, okay, at this position, okay. It will neglect the other side, okay. So click OK, and you will have a unit cell like this, okay.
Sarosh, I did use actually to use the 3 by 3 the default, but from where we can increase the number of the cell.
For increasing the number of cells, you just need to select this one, and you can copy paste, okay, like this.
No, I know this way, but there is no another way just to increase 4 by 4, 10 by 10 or something.
Let me check, but I did not use any other way. In this way you can increase.
Yes. But I guess maybe there is a way to write maybe 3 or 4. I remember it was in the base array, but I don't know, I forgot it.
Okay, let us check. Maybe here we find.
Because I did use 3 by 3 is this the default. If I need to increase, I know how to transfer it.
Maybe then you don't need to use the unit cell because it is only for one, okay.
Look at these unit cells.
Wait a minute.
No, it was in the first array. I think that you can increase the number of it.
No, but here you must just I never see it, this option.
I remember in the phased array, I remember once I used it.
But in phased array, Muhammad, it is just the change the phase, I think.
No, I will just change the number of cells.
That's a new idea. I didn't see.
Even I did not see in this here.
To transform, I know it. We can transform, the can be increased. Okay, thank you. I will check it and I will.
Okay, so we have a port here. Okay, we can change the direction of the port. Okay, like we have x, y, z plane. Okay, like this one. Okay, we have x plane. Okay, this one. We have y plane. Okay, we have z plane. Okay.
But Mr. Ahmed, I think to put the port is depending when you put open in the boundary condition. You put the port. You can choose any directions.
But here you can see I have used port in front of the radiator. Okay.
Yes, but in this case, in boundary you put open at the
must be open.
Yes, we can.
Because must be to be open.
Yeah.
Okay, let me share one more thing. Okay, in this case you have a port in front of the radiator. Okay, and there is a formula for the distance of this port from the radiator. Okay, so this is the formula. I will share with the CST. I will share you with the CST file, and you can calculate with the formula. Okay, so here we have a D reference. Okay, the TP is the same. TP means thickness of the patch. Okay, and the D reference, where is the D reference? Here we have a D reference, this one. Okay, we have a T 14.11 the size of the substrate. Okay, the length or width, whatever. The other one is the thickness of the patch. Okay, and then we have a thickness of the substrate and thickness of the patch. Okay, so here you see we use minus D reference. Okay, plus TP plus 5.52. Even if you increase or decrease, like I mean the size, sorry, gap. Okay, like even if you simulate at this position or simulate at this position, it will not affect much your results. Okay, I simulated and tried many times, but it did not affect my results. So in the case of the, if you are not using the ground plane, suppose I am removing the ground plane. Okay, and I only want to simulate this EBG cell, so I need to change the boundary conditions. Okay,
but Mr. Ahmed, when I choose time domain and change the position of the waveguide port, I get different results.
What can you repeat?
When you change the distance of the port, I get different result when I use time domain solver.
You are simulating in time domain. Why you are simulating in time domain?
Because many people use time domain. For that, I start from time domain.
No, actually, for the unit cells, they are all designed in the frequency domain. When you are dealing with the antenna and the unit cell together, then you use this one, this time domain. Okay.
And because I start from article, they use time domain. For that, I start from time domain. I didn't use frequency domain.
Don't know, but you can send me that article to check. Okay.
Yes, there are many actually.
Okay. Now we can let's open any design CST file to place the AMC between back the antenna. Okay. Suppose.
I think brother Tarek, maybe the people estimate something about dispersion. I think is related to it. I think
until this file of MATLAB for SRR, when you converge to CST, they use the time domain, not frequency domain.
Maybe they estimate something about related to the dispersion.
For Hassan, for this MATLAB body, they use time domain. For that, I confuse. And the second confusion is about when I want, Mr. Ahmed, I want to put these unit cells in the patch or the ground, like not like a reflector or substrate. You understand me?
What you are saying?
I mean, when I want to put these unit cells in the patch,
Yes.
like isolation between MIMO antenna. When I simulate this unit cell before I put in antenna, what the boundary condition I must choose?
For the unit cell you are talking about, or for the antenna you are talking about?
I mean, for unit cells before I put it in antenna. I will tell you why. When I want to miniaturize antenna, I have antenna work at 5 gigahertz. At 5 gigahertz, but I want to use it at 2.4. So, dual band. You understand me?
Wait a minute. Let me place the unit cell behind the antenna. Okay, then maybe you will get the answer, or maybe I will understand your question. Okay.
Okay.
Let me find an antenna here. Where is antenna? Okay, this is UWB. Okay, this is the unit cell. Okay, even if you want to make array of this unit cell in this CST file, I mean in this case, okay, you can copy this one. Okay, copy this one and paste in this file. Okay, and even if you want, you can copy this one, this component file, this one. Okay, this one, and paste in this here. Okay, here, and you can make array here. Okay, if you want. But you need to check the size of the antenna first. What is the size of the antenna? I have size of the antenna here, like this one. Okay, the length of this antenna is about 50. Okay, suppose 50, and I need to check that how many arrays I need. Okay, okay, so we have 14.8. Okay, and if we multiply with 5, okay, we get 74. If we multiply with this one, the size is smaller. Yes. Okay, and if we cannot take half. Okay, so okay, so I need array of 4 cross 4. Okay, mean I need 4 cross 4 array of this unit cell. Okay, to keep this unit cell behind this antenna. Okay, even if you make the array and simulate here, you will get the same results. Okay, but it will take more time simulation. Okay, we need 4 cross 4. Okay, so we are converting into 4 cross 4. Okay, first create the rows. Is this connected or not? Okay, now we will move downward. Okay, we need 4 cross 4. Okay, now we have a 4 cross 4. Okay, so it is better if you add all these, like you have a ground plane. Okay, these are your ground plane. Okay, select all these one. Okay, and add in one. Okay, press shift plus button on the keyboard. Okay, then it will add your all the ground planes. Okay, because uh, when you copy this one, like all these, you will see you have so many components here. So when you paste here, it is hard to select the components. Okay, so if you add all these components, there will be three components. Okay, there will be three components. The first one is ground, the substrate, and the patch only. Okay, but here in this case we will have, okay, so let's forget. Okay, so where I want to place this unit cell. Okay, sometimes we take let me draw here. Okay, suppose this is your antenna. Okay, sometimes we place the antenna like you place your WCS, you know WCS, this is your WCS, this one. Okay, so sometimes you place the WCS at this position. Okay, at this position, so that when you place the metamaterial, it will be like this. Okay, this is your sorry, this is your metamaterial. Okay, that is means the lower edges are the same of the antenna and the metamaterial. Okay, and sometimes we use like this is your antenna. Okay, and you place the WCS at the center of the antenna. Okay, and then you paste the metamaterial, and your metamaterial is like this. Okay, okay, so there are multi ways you can apply and choose any technique. Okay, but you need to simulate with which technique you are able to achieve get good results. Okay, I have seen many papers, sometimes they use this one, sometimes they use this one. Okay, and in my paper I have rotated the metamaterial. Okay, as you know, like this is the metamaterial, I have rotated, not this. Even I simulated the metamaterial like this. Okay, this is in my paper, but even I simulated the metamaterial like this. This is my antenna. Okay, and I place this metamaterial like this. Okay, mean center of the substrate of the metamaterial. Okay, so even I did not get good results with this one. Okay, so I tried with this one. I face a problem of the single frequency band, so I neglect this one. I tried this one, I even did not get good results. So I tried this one, I get good results. Okay, so you need to try multi times. Okay, even you need to increase the length, I mean the distance. Where is the distance? I am talking about this distance. Okay, so you need to simulate your unit cell with some distance like 5 millimeter, 10 millimeter, 15 millimeter. Okay,
because you make the ground away.
what?
Because in all other cases, I think because you make the ground of antenna away from the structure of the meter material.
Yes,
Because,
you are talking about the ground plane of the antenna.
yes, because in all cases what you show to us now, I think it's included the ground plane.
Okay, let me explain. As I think I discussed this one in the previous lecture, that if you want to use the metamaterial, you need to use the CPW technique. Okay, or partial ground plane. Okay,
I got it.
yes. Why? What is the reason? Because you as you know, in the metamaterial, when we have a full ground plane behind the antenna, then this reflector, this metamaterial will not work properly because all the radiations are in this direction of the metamaterial, and you have an antenna here, and there is a full ground plane behind the antenna, and this ground plane cancel these effect. Okay, so that's why.
Is there this makes sense when you use foreground plane?
No, this information I know it, Brother Saroj, but I mean about it. You said you failed 3 times, because if you check the 3 times which you failed, you know, slide 15.
Slide 15. Yes, this one.
You said you try the first one and second one. I think maybe it's a common between all of them.
Yes, this is common. This is the
yes.
This one is common method. Okay, in all the papers.
I mean your ground plane is inserted or be included in all these 3 trials. But the other one you make it away a little bit from the meter material. Maybe this is a change.
No, I mean just I am talking about just the antenna and the metamaterial. Okay, I am not talking about the ground and other thing. Okay, every case are similar. Okay, just you see there is a patch ground and copper. I mean patch ground and substrate of the metamaterial.
Maybe you don't get what I mean. I will send you by WhatsApp.
Okay,
Sorry.
okay. Dear Tariq, do you have any question? You are asking saying something.
Mr. Ahmed, this all design that you make is for improve the gain, is it?
Yes, I mean, yes, it will not affect surely the, I mean, suppose your frequency band is this one, okay, and the frequency will remain the same even if you are using the full ground plane, okay, and but there will be no increase in the gain, okay, because there is no ground plane, how it can reflect the radiations to the other side of the antenna, because if you are not using the ground plane, like you are not using the ground plane and you are using the CPW here, okay, at this point, okay, and surely these radiation will be come at this point, okay, it will radiate your, I mean it will improve your radiation pattern, okay, in this direction.
Yes, I agree with you.
So
Okay.
yes,
But when I want to use this unit cell on the patch or on the substrate, I mean for miniaturize the antenna. I mean I want to design antenna work at 5 gigahertz, but in the same time I want to it work at 2.4. So in this case, I must increase the antenna, but I want to use these unit cells on the patch to make dual band. You understand?
no.
like slot to make to get dual band.
In the unit cell you are talking about, you are saying that what?
I mean, there are many articles for miniaturize the antenna. They use these unit cells, metamaterial on the patch.
Oh, okay. Now I understand. Maybe I can answer in other way. Like suppose, okay. Now let's paste this one. Then I will let you know. Okay. So let me. Okay. So this is at the center. I mean at the edge of this antenna. Okay. And we have an AMC plane here. Okay. Let me select the center. I cannot select the center one because my WCS maybe not selected this point. Okay. Let's check this one. Okay, now yes, it is selecting. Okay, so I remove the dimension. Okay, so I am copying. Okay, press Control C. Okay, and here you have a WCS. Okay, now you need to turn your WCS, I mean shift your WCS at first at this point. Okay, the same. Okay, at this point click apply. Now you move 5 millimeter away. Okay, 5 millimeter away. Okay, so I click 5 millimeter here. Now click OK. So my metamaterial will be at a distance of 5 millimeter. Now I am pressing this, I am clicking this one. Okay, now I am pressing Control V. Okay, and you see, okay, so you have a metamaterial. Now after pasting this metamaterial, you need to press the escape button of the keyboard. Okay, okay, so you see this is the one. Okay, now I if I your answer, the question of your answer, Mr. Tariq, you want to miniaturize the size of the antenna. Okay, I have realized that this metamaterial is bigger than the size of the antenna. So even if I cut this metamaterial like the size of the antenna. Okay, let me move my WCS here. Oh sorry, okay, let's make one copy. Okay, I am adding all substrate. Okay, now I am adding all patches. Okay, to make it one. Okay, now I am adding all the grounds. Okay, okay, now I have 3 layers. Okay, so I am selecting the substrate, okay, of this metamaterial, so that my WCS is at the center of this substrate. Okay, now I can use this one, this curve. Okay, now I will create the boundary of the size of the antenna. Okay, so this is my boundary. Okay, I will show you my another paper in which I use this technique. Okay, so I shift my okay. So what I am doing here, I want to cut my metamaterial. I want to keep the size of the metamaterial same as the size of the antenna, okay, because this side these sides are additional, so I don't need this. I want to cut this one, okay, so I can cut this one, okay, by creating the boundary as I done like this, okay. Okay, you can keep any dimension, okay. Okay, let's take 3 1, okay. Now I am shifting my copper. This is the copper, okay. This is the same size of the additional patch, okay. I mean this additional metamaterial. Let me later shift on this way, okay. Okay, now I select the ground patch substrate of the metamaterial, okay. Now I am pressing minus button of the keyboard and select this one, this boundary, and press enter, okay. Okay, now you can see here the size of the metamaterial are of the same size of the antenna, okay. It will work same as the previous one, but you need to check, you need to simulate, you need to check either is there any change in the results or not, okay. So in this way you can miniaturize the size of the antenna, okay. I have published one paper that is also on metamaterial. I cut the substrate, okay. Maybe this, there is electronics, yes. Not this one, an artificial magnetic conductor.
I send you, Mr. Sarosh.
Okay, I check it now.
What I mean.
This is from the paper, yes. This is very nice design. Okay, let me download this paper and talk a little bit about this paper, and then we will discuss about your talks, okay. Okay, so I am just want to show you that this is the size of the antenna, okay. Here I use the partial ground plane, okay, with these slots, okay, and I use the metamaterial here. This is the AMC unit cell, this one, okay, and I use the size of this metamaterial, this one, okay. You can see here I designed the unit cell same size of this antenna, okay, the same width of the antenna, but I use one full and one half plane of the unit cell, okay, to keep the size of the antenna compact, okay, because there is a main problem nowadays, because with the metamaterial the size of the antenna is increased a lot, because in the previous research mostly people offer or say that the unit cell must be of in order, like 3 by 3, 4 by 4, 2 by 2, okay. But here we did check that if even we are use the same size of the substrate, I mean metamaterial of the antenna, then we get the same results, okay. I mean what is the main purpose of this metamaterial? To improve the gain, to miniaturize, not miniaturize in this case metamaterial, okay, to improve the gain and to improve the radiation pattern, okay. If you are achieving the same things even with this one half metamaterial, then you can claim that your metamaterial is still working, okay. So in the you can also try this technique, okay. Okay, so what is, let me check your question. Okay, this is the design, yes. Okay, now you can ask the question. What is your question?
You saw the design?
Yes, I am looking at
I mean, they use these unit cells for
let me wait a minute. Let me also show in the screen so that others can understand. your question. Okay, yes, this is your question.
Like here, they used for maybe for isolation
SRR,
between
yes.
the antenna.
Yes.
But I want to know when I simulate these unit cells before I put in the antenna.
Yes.
What the boundary condition I used in the port.
Okay, now let me explain. Okay.
Y or X.
Let me explain. Actually, they in this design they did not simulate the unit cell. Okay, they did not simulate the unit cell, but they are calling this design that this is a metamaterial based antenna. Okay.
People do this process actually.
Okay. Yes, you can.
But he didn't show us the properties of the metamaterial.
Yes.
Sometimes.
Okay, let me explain. Okay, in some papers they call that they have designed metamaterial based antennas, but in actual they did not simulate the unit cell. Okay, they have used this SRR. This is the technique, their CSRR. Okay, complementary split ring resonator, and the SRR. Okay, split ring resonator. Okay, so both are almost the same. Okay, this is the like you have a rings here. Okay, not a completely ring. Okay, let me remove this one. Okay, so this is your ring. Okay, and this is your another ring. Okay, so this is called SRR. Okay, this it can be or multi like a rectangular, okay, shape like this.
But actually it's similar to the 50 grounds.
What?
They sometimes they use it as a metamaterial, but actually they use it as a defective ground structure.
Yes, they use and that's why, and also this one works same as in the like to improve the gain, because in SRR it is very helpful to increase the gain and improve the results. Okay, and most of the researchers do add these slots or in the radiator or sometimes in the ground. If they add these type of slots in the ground plane, then they call that they have designed the metamaterial like that. Okay, but this is not actually a metamaterial based antenna.
The ground structure is one, I guess.
Yes, so in this
is metamaterial. This is
this
metamaterial because when you simulate in antenna, you will get epsilon and mu negative for these unit cells.
Yes, so but this is not, this design is not actually a metamaterial based antenna. They just add the SRR technique in this design. Okay.
I have confused between when I used for a slot or I used as substrate or
this is the kind of defective ground structure.
Yes, this is a defective ground structure. Is shaped just like a metamaterial. That's why they call that this is a metamaterial based antenna. But actually, as I told you, this is not a metamaterial based antenna.
The people of the MIMO also using this kind of structure.
Yes. So don't be confused. Okay. Don't worry.
Yeah.
Don't be confused.
Is the metamaterial when we can say this metamaterial or
okay, you can say this is a metamaterial. Okay, let me have a snip tool of this picture.
Because the definition of the metamaterial is not to get epsilon and mu negative.
This is not a metamaterial. Just they are calling it metamaterial because of the maybe SRR technique. Okay, so you have a design here. Okay, you they have created this. Maybe let me check the other side of the antenna.
It's another term.
Okay, maybe yes. Now in this case, actually they did not. You did not see any unit cell simulation in this case. Did you see any? If you only, I mean, they did not simulate the unit cell in the paper?
Actually, I simulate SRR like we have in the paper.
Okay. Now here, if you have a look, maybe you see this one. This is not exactly in the case of the
first image is I think just for isolation between the antennas.
They may be called this antenna metamaterial because of this one, this one. Okay.
Yes, in the ground plane.
Yes, maybe. Okay, not because of this one. I thought you are talking about this one. Okay. They did not call this design metamaterial because of this one. Okay, but in this paper, if you see this one, then you can say it is a metamaterial based antennas. Okay. These are different designs, right? Yes.
Yes, different. I get this image in Google.
Yes. So in that case, yes, it is different, because here in this case maybe they did not use the ground plane. Okay, but here they are only introducing.
Mr. Salar,
Yes.
I will send you the link. Is of this deep.
Your voice is lagging. Dear Muhammad, can you hear him? Can you hear him?
No, I don't hear him. I think something happened to Tariq's voice.
I sent you the link. Can you hear me?
Yes, yes. Yes, they are working on metamaterial. Tariqul Islam. His main research is in metamaterial from Malaysia.
Yes, he's originally from Bangladesh. He's originally. I know he's my close friend.
Mm-hmm. In this paper, they did not simulate. Yes, this is the result of the metamaterial.
Actually, sometimes they use it as I said to you, brother solution, something like frequency selective, as they use it as a filter.
Mm-hmm.
They use a part or maybe another name, frequency selective and absorber. We're dealing with it as a filter, special filter.
Mm-hmm. Okay, also send me the link of this design. Okay, this one. Okay, in some design, even my partner, I mean my friend in my university lab did work on the implantable antenna, and he did not introduce any metamaterial or simulate any unit cell. He just created a small patch, okay, on the back side of the substrate, okay, of the antenna, and just call them this is a metamaterial based antenna. I was really confused. I asked him, did you simulate this unit cell or not? Why you are calling this metamaterial? He told me that this is another type of the metamaterial. We do not simulate this unit cell, and we just add small patches on the ground plane, just like that.
You know, the resolution, when they start maybe the terminology of metamaterial, the people start by SSR. Yes, I remember that. I read many people. They said it is a metamaterial.
Okay. Yes. In most of the, whenever you see any metamaterial, you will notice a change. I mean shape like this. Okay, like this one. So that's why in most of the techniques they have used SRR technique as a metamaterial. Okay. Let's check this paper.
Actually, brother Tariq, you don't need to I think you don't need to read an MBDI journal. Actually, I start not trusting them too much.
What?
No, about MBDI journal, because I think sometimes the reviewing is not good, I guess.
No, but when I see his name, Muhammad Tariq Islam, I think.
No, Muhammad Tariq Islam, yes, he's good. He has a very good, maybe scientific reports and something like this.
For that, I follow. When I get this name,
MBDI, sometimes you need to become careful when you're reading the review. Some paper is good, but you need to become careful.
Okay. You can scroll down, Mr. Ahmad, please.
Yes.
Here, you can see the port when he changed the port.
Did he add the?
Like Z-axis. It's not like Z-axis in X and Y axis. It's a problem for me. I can't understand why.
Yes, for what I said to you many times. Sometimes they change it out, but also it depends on the application, I think.
Did he introduce the where he placed the antenna?
Yes, he put behind the antenna.
He used two times. One at the center of the, I mean behind the antenna, and also the other side of the antenna. on the second side, opposite side of the substrate.
Yeah.
This is, yes, this is the metamaterial, okay, and also this one, maybe they use the same design but simulated two times, okay. Here in this case they maybe they use the different ports, okay. Maybe you see the left side and the right side and the top side and bottom side, okay. They simulated this unit cell two times, okay. For one time to place the metamaterial behind the antenna, and for the second time they to keep this unit cell on the other side of the substrate of the antenna, okay.
I send you the common article for isolation for MIMO antenna.
Yes, this is of Amjad Iqbal. He is my friend. He's Pakistani.
Is common article. They use unit cells between the MIMO.
Yes, this is what I am talking about. Yes.
It's a kind of the 50 ground structure. I take this paper as my reference to compare. It's a kind of the 50 ground structure, I think.
So in this case, we can say this is metamaterial.
I think so. For me, it's a kind of the 50 ground structure for isolation.
Wait a minute. You see, actually, let me explain one more thing. Okay. So for those who confused, okay, this is what, this is metamaterial, okay. Suppose this is main branch and it has subcategories, okay, like FSS,
substitutional,
EBG.
Yes.
Okay, and other what we have, AMC.
And meta surface is the same.
Yes, this is the same. Metamaterial, meta surface, same. We can also say meta surface, and we can also say HIS. There's many names, okay. So combinedly the single name is MTM, okay, metamaterial. That's why in some papers you see why this metamaterial is different to the other one, okay. So in that case you can say they just use the general name, okay. So this is the general name, okay. This is the general name. So
and we have the double negative refraction.
Also we say SRR, okay, technique, okay. Also we say DG.
Photonic gap, also I think.
Okay, discrete ground.
Photonic crystal. Yeah.
I am nowadays working on projects on photonics integrated circuits, okay.
BGP, photonic gap.
Okay, so there are many names, okay, so don't be confused, okay. The general name is the metamaterial, okay, so that's why they have called the metamaterial. Even they have applied the EBG structure, okay. So in EBG structure we mostly
in this case,
yeah.
Sorry, Mr. Ahmed. In this article they use HIS isolation. They use HIS like a metamaterial.
Yes, I read it. But Brother Targa, I prefer to maybe not to go too much to MBDI. You know, the journal is better than even the other scopus. And only one of them is ISI.
What do you recommend for me?
Actually, you have account in Web of Science.
No.
Anyway, I will send you a link. But yes. First of all, you need to sign from the official account of Web of Science to have this access.
Okay.
Where it is written that they have used the HIS technique?
Web of Science is better. You can have a good journal, I think. Even the Bears journal also, they have a very good article. They are careful, Bears journal, than MBDI. They are very careful.
Okay, what I understood is that in most of the cases, if you what you are talking about here, where is the HIS? You told me it is
HIS in this case is this metamaterial is act like HIS. It's act like height impedance surface between the antennas.
Did he talk about here? I don't think where he talked about this HIS. Did they define any?
He just used this structure for isolation improvement.
Yes.
Isolation is HIS.
Okay, so maybe in HIS we can use they maybe they have used you see this is a metamaterial, okay, but in HIS maybe we use less number of cells of unit cells, okay. In the case of the unit cell we mostly take whole it can be integrated inside the substrate of the antenna, they mostly use EBG in complete surface of the in complete size of the substrate, okay. The same size of the substrate, okay, and also in metamaterial and AMC back we use the same size of the antenna or maybe larger, okay, but here in HIS maybe they use small less number of unit cells, okay, just to get some difference in results, okay, to improve maybe they introduce this technique to improve the mutual coupling of the MIMO antenna.
Actually, Mr. Sarosh, until after they used this metamaterial, he didn't get good isolation. I saw in the result, not good result.
And any difference? Did they compare any results with
small difference, just small difference, not big difference.
This is the P gain, no difference in the result. No much difference. Okay, and
the gain is not good.
Even
also I take it as in the comparison table with me this build.
Then why they have introduced this technique? Okay.
I don't know, but that's the journal of the pairs. All journal MMP and the main journal all better than this journal.
Okay, if you do not find any improvement in the results, then no need to use metamaterial. Then metamaterial is useless.
Yes. So I think I saw one paper for you in pairs. I remember I read it maybe 1 month or 2 months ago. Progress in electromagnetic research.
Mm-hmm.
I think it was MP or something like this. It is a good journal actually. Okay, so we have finished our last lecture on the metamaterial, and what we have tomorrow we will discuss. Did you download these softwares that I shared the links of the Origin Pro, Sigma Plot, and other MSVs?
Yes.
Okay, sometimes I am facing some license issues. I will try to fix the problems, and I hope tomorrow we will have a now from tomorrow we will have very interesting lectures, okay. Because now it's your turns to work on. So we tomorrow you need to give me ideas because I just updated the maybe this is not this one is I updated the schedule, okay. I removed some more, increase the number of days, okay. To reduce let me see here.
For today, tomorrow, you will use Origin or Sigma Plot?
From tomorrow, tomorrow I will discuss every software, okay. Because tomorrow we need to finish only the tools, okay. This is the updated schedule. I will share again, okay. Tomorrow we will discuss about the professional graph tools, okay. And then I also prefer to remove this one, okay, because it is just a design selection, group selection. And tomorrow we will if we find time, then maybe today you have a time. Today you need to decide which on which type of the antenna you want to work, okay. So you need to send me an email, or you can tell me by WhatsApp, okay. And you need to propose me an idea, okay, like I want to work on this project on this design, and I have an idea. I can work on it. And even if you want to work on any type of the antenna and you don't have any idea, don't worry. I will share the idea with you, okay. So from tomorrow we need to speed up our work, okay? We because we have less time, and in this time we need to target some high quality journals, and surely inshallah we surely will publish, okay? Don't worry. Whenever somebody work with me, I always help him to until the paper will publish, okay? So we will surely publish. Even you are beginner, whatever you are, we will target good quality journal, and I will try my best to help you as much as possible, okay?
If you just give us about maybe half an hour about RFID.
For the
Half an hour, no more, just a simulation.
let me check if there is any design here. I had a design, but I think I deleted the folder.
Even I read the design, just a simulation and how we can.
Okay, the simulation is the same as of the antenna, but just a little difference.
Cross-section, no, you need to adjust the radar cross-section option, I think, in this point.
Let suppose actually we use gap. I mean, fill the gap with vacuum. Okay, in RFID. Okay, I had a design, but I lost the file. Maybe I will find and send you. Okay, but because I did work with Mr. Ihab on one project. I mean, 1 year ago, on one student of one MS student, he did his work on RFID. Okay, I will ask him to share the file with me again. Then I will maybe I will explain. Okay.
Okay, thank you. So, even if it is difficult for you, just we can make a video for us, almost maybe 15 minutes.
Or maybe Mr. Ihab has a video. Or actually, maybe one girl told Mr. Ihab that she wanna work on RFID, and she wants to have a course on RFID, and she I think she posted in a group a poster on RFID. Maybe Mr. Ihab will give an important session on RFID, a course, a complete course.
Okay, thank you.
For after this course, I am again thinking to have a course, but only on specific field of the antenna, like only on antenna arrays, or only on implantable antennas. Okay.
Can you put on modeling antenna?
What?
Modeling antenna.
What? Okay. You are talking about equivalent circle modeling. Yes. Yes, I am thinking. Yes, for the next course, I am thinking of the ADS software. Okay, maybe on the equivalent circle modeling and the special types of the antenna. Okay.
Yes.
So for now, this is the combined. Course. I hope we will. Let me stop the sharing. It will become longer.